it's probably, I don't know. Anyways, it's the approximation of the area below the bar graph. I mean, the graph with the bars. Like
Okay,
split it
yes.
in half.
Yeah. Remind me tomorrow. Sorry, the computer just asked to update. Right, so for those at home who couldn't hear, the question is about this idea of we've got some weird function, it's doing its thing. We want to approximate the area underneath it. So what we can do is we can say, all right, let's first pick our interval. It's going to be from A to B. This is x equal to A. This is x equal to B. So we've got our interval, we've got our function, we've got our graph. Now we want to break this interval up into equal subintervals, or subintervals of equal length, we should say. So we're going to say, all right, we want n number of subintervals. Then what that means is the length of each of those subintervals, delta x, is going to be equal to the length of our interval divided by n. Because this just breaks it up into n parts, right? So for our example, let's say n is equal to 3. Okay, so this first point that represents the end of our first interval and the beginning of our second interval, it's going to be a plus delta x. The second one is going to be a plus 2 delta x. And that makes sense, right? Because what we're saying is we want to go delta x from where we started. So we start at A, we add delta x. Everything in here gives us our first interval. Now our second interval is going to be from A plus delta x to A plus 2 delta x. That's going to give us our second interval. It's the same length, though, as the first. And then we're going to do it again for the third interval, right? So one thing we can note on here is that A is equal to A plus 0 delta x, and B is equal to A plus 3 delta x. So just to verify that this is in fact equal to B, let's use our formula for delta x, and the fact that we're here choosing that n is equal to 3, just to double check that this works out to be equal to B. So delta x is equal to B minus A, all divided by 3. So A plus 3 times delta x is equal to A plus 3 times B minus A divided by 3. The 3's are going to cancel. So we have A plus the difference between B and A. But now we can drop the parentheses and the A's cancel. So we're left with just B. So everything looks good so far. Now, we're going to make up a rule about how to pick an x value inside of each of these intervals. Rule can be whatever we want it to be. It could be the far left point of the interval, the far right point of the interval, the midpoint, any point, really, as long as it's inside of that interval. For the sake of simplicity, let's choose the midpoint. In our notes, we represented this as X star. This particular one would be X star 2. This would be X star 1. This over here, be X star 3. So the index represents the fact that we're choosing an X in our first interval, our second interval, third interval, right? So now, what we're going to do is we're going to say, all right, what's the value of our function at each of these points? This is f at X star 3, f at X star 2, and f at X star 1. Now from here, we're going to make rectangles of the height f at X star in these intervals. So that's going to look something like this. Right? Now from here, we're going to find the area inside each of these rectangles. Well, the area of any one of these rectangles is going to be delta x times f of X star, right? In this case, it's area 3, so we're using X star 3. This thing is equal to area 3, right? And the reason why is because we've got a rectangle of width delta x and of height f of X star 3. Now we're going to take and add up the area of each of these rectangles. So A1 plus A2 plus A3 is equal to the sum from n equal to 1, and this board is not erasing well. That is hard to read. Let me try this again. A1 plus A2 plus A3. This is equal to, using that summation form that we talked about before, that is the sum from n equal to 1 to 3 of delta x times f of X star n. And just to expand on this a little bit, this thing is equal to delta x of f of X x1 star plus delta x of f x star 2 plus delta x of f of x star 3. So it does in fact do what we want it to do, right? Folks at home, can you read this well? Yeah, it looks
Yes,
good.
we can.
Awesome. Cool. So, now notice each one of these stars, or each one of these terms has a delta x. So we can factor out that delta x. And multiply the sum of each of our f of x stars. And this thing, as a whole, is going to be approximately equal to the integral from a to b of our function f of x integrated with respect to x. And this is the entire process. This is the idea of it. We're starting off with our interval from a to b. We're breaking it up into n many parts. Then we're choosing an x value inside of each of these intervals. Then we're using this information to get our f of x stars. And saying, all right, what's the area then of each of these rectangles? Now add up that area. That's going to be approximately equal to your integral. Having said that, notice we take the limit as delta x goes to 0. What we're saying is n's got to go to infinity, right? So we would have in that case an infinite number of these rectangles. That sum wouldn't approximate, it would be equal to the area under our curve. And that's the whole idea behind this thought of approximating the area under the curve. Did that answer your question? Yep. Folks at home, did that make sense?
Yep.
Yep, awesome. So, with that having been said, what other questions do y'all have? What other things do y'all want clarified? Okay, let me check WebAssign really quick. See if I can pull up a couple good problems. That's not what I wanted, is it? Yeah, it is. Cool. All right. So it reads by category. Don't read on that one yet. So it looks like we're scoring about evenly across all of these exams. About the same. So let me go about this a slightly different way. Of all the material that we've gone over so far, what seems to be the most difficult to understand? What's the thing that you're just like, what the fuck?
the present value question is pretty difficult for me. I think that's in 6, I think.
Okay,
But I'm just wondering, like, with the information that they give you, in a problem here, can that information be determined through a financial calculator? I'm just kind of curious. Because
I guess I don't know what a financial calculator is.
so with a financial calculator, you can put in present value, future value, number of years,
Then it should be
payments
able to.
per year, things like that.
Then it should be able to.
Because I tried, I was just wondering if it would work, and I couldn't seem to figure it out.
All right, so. Question 27 on week 14.
Yeah.
All right, let's pull this up. My bad. Clicked on the wrong. All right, so question 27 gives us 2 different graphs. And it's about a state legislator debating what to do with taxes. So, something pretty prescient for the times, right? Since that's 90% of what the debates are right now. And they look something like this. Make sure I'm drawing this right. Right. This top one is proposal 1 and proposal 2. And our graph is time and deficit. So about to misspell that. It is a second I. Awesome. Deficit. Fun fact, mathematicians suck at spelling things. So the question goes something to the effect of a state legislator is proposing is debating 2 different proposals on how to handle the state deficit over time. And if we look at the deficit as a function of time, their graphs would look something like this. Now the question wants to know which one of these 2 proposals are the best deal. So with that in mind, the question comes down to what does it mean for something to be a better deal? Well, if we're trying to handle the deficit, then the best deal would be the deal that requires the least amount of spending, right? So in that sense, one way we can go about this problem is by looking at the area under the curve and trying to minimize it. The deal that would minimize the area under the curve would require less spending over time. So here, the best proposal would be proposal 2. Assuming, of course, that all we cared about was minimizing the deficit and spending as fast as possible. If we had other considerations, we might make them accordingly. But just considering the actual cost of taking care of the deficit, the question here is all about minimizing the area under the curve. Because the area under the curve is related to the amount of spending related to the deficit itself. More deficit over time means more spending. So the faster you get rid of your deficit, the better. But if that's the case, then you want the graph, the function that approaches 0 as fast as possible. But if your function's approaching 0 as fast as possible, then that means the area under the graph will be smaller than the other areas, than the other functions. Make sense? So in this case, this question was more about a conceptualization of the problem than it was about the actual math, right? Like it wasn't asking you to calculate anything, it was asking you to show a comprehension of the material. And really, that comes down to your understanding of the question itself, and it is a poorly worded question, I do admit. Folks at home, does that make sense?
Yep.
Cool. So this was week 13, number 27. What about y'all at home? Do y'all have any questions or any areas in this class so far that you, up to this point, throughout the entire semester, has there been anything that you're like, oh, what the hell? Awesome, then everyone's gonna ace this final. I'm loving it. When I was just looking at the exam grades, there wasn't any one exam that stuck out as needing to be reviewed. So that kind of leads me to either pulling up the study guides and just going through chapter and chapter, or just letting y'all ask questions. Which way do y'all want to go about this?
I think a variety of different questions from different chapters. Things would be a good place to start.
I think you are correct. Previewer, go back. All right.
Sir, I have a question.
What's up?
Yuck.
Hello?
I'm listening.
Yeah, question 7 of the last assignment that was submitted yesterday. I don't know, I just couldn't quite get the answer. That's for present value.
Yeah. I think that was number 7, yeah, last week, yeah.
Sorry?
The other student in the classroom was verifying that it was question 7. He was saying he was having the same question. He had
Oh, okay. Okay, I didn't hear him.
Give me just a second to get this all pulled up. zoom in so I can see it from the board. All right, so question 7 gives us our C of T. It gives us our R as a percentage. And it gives us our time, right? And we know present value is equal to the integral from 0 to T of C of T times e to the negative RT dt. So, in the example as it's given on my computer right now, we've got C of T is equal to 26,000 plus 400T. Yeah, 400T. The percentage is 7%. But we need to convert this into a decimal. So converting it into a decimal, that's 0.07. And time is equal to 5 years. Make sure I'm not missing anything from this problem.
Oh, well.
So from here, we've got everything we need to set up the problem. Plugging everything in, we're going to leave 0 as it is, replace T1 with 5. CT is that polynomial up there, 26,000 plus 400T times e to the negative r, which is 0.07, t dt. Now, the first thing to notice is we can break up this integral into 2 different parts. Once we simplify this, or once we expand this out, I mean, we're going to be able to break it up into 2 different integrals. So to make more room, b is the integral from 0 to 5 of 2,600, my mistake, 26,000 plus 400 times e raised to the 0.07 t dt. All right, so expanding this, we have the integral from 0 to 5 of 26,000 times e to the negative 0.07 t plus the integral, my mistake, plus, I'm going to do that in a second, plus 400t times e to the negative 0.07 t. All of this is integrated with respect to t. So now we can break this up into 2 different integrals. The first one is from 0 to 5 of 2,600, 26,000 times e to the negative 0.07 t dt plus the integral from 0 to 5 of 400t e to the negative 0.07t dt. Now we can bring out the 26,000 and the 400. To get 26,000, the integral from 0 to 5 of e to the negative 0.07 t dt plus 400 0 to 5 of t e to the negative 0.07 t dt. Now, this integral, we're going to have to integrate by parts. This one we can do using u sub. So after u substitution, you're going to have to rewrite all of this, right? My mistake. You're going to apply by parts and then u sub. And solve it that way. Does that make sense? Does that answer your question?
Yes.
That's awesome. Cool. So a point to make in the notes, when we took time to go to infinity and we took our function ct to be a constant, the result came out to be the same to a point. It came out to be the principal value divided by the rate, right? So when time goes to infinity, this thing changes a little bit, but not a whole lot. Cool?
Yep.
Any other questions about all of this? No? All right, now I'm going to go to the study guides. I'm going to try to pull one problem from each chapter. Minimize that. Holy hell, that Zoom was too big. I think for the most part, we got all of chapter 1, right? Folks at home, did y'all need me to go over anything from chapter 1? Well, I'm going to go over some of these limit problems. So I think that would be a good quick review. Because it's been so long since we even talked about limits. Let's find a good limit right there. All right, so from chapter 1 study guide, number, what is that, 51? Yeah, 51. We are asked to solve the limit x goes to 7 of x squared minus 9x plus 14 over x minus 7. X squared minus 9x plus 14 over x minus 7. Now, the first thing we want to do here is going to be to simplify this as much as we can. And the way we're going to do that is by factoring out the numerator. So the numerator here can be factored as the limit as x goes to 7 of x minus 7 times x minus 2, all divided by x minus 7. Now, when we do that, notice we get a cancellation here. So this thing is equal to the limit as x goes to 7 of x minus 2. So from here, we can just plug in 7 and get 5. Now, why does this work? What's happening here? First, why couldn't we apply the limit directly to here? And then second, why did this move help us? Well, the reason why we couldn't apply the limit directly is because 7 minus 7 gives us 0, and we'd have a 0 in the denominator, right? And that's not allowed. And the reason why this move helped us was this move allowed us to say, all right, this is a 0 that's being forced into our equation. The way this problem's set up, we have a removable 0. Because we have a removable 0 and a removable hole and our function, we can now go back and apply the limit after we take care of it. Make sense? So all we're doing here is we're saying, in this first case, the graph of this thing looks something like that. In the second case, after we remove the 0, the hole, the graph looks something like this. And the limit is asking, what happens in your x value, in your y value, as your x value goes to 7? Another way of saying it is, as you squeeze into this hole, does x in fact go to 7? Make sense what I mean? So in that way, all this move is doing is saying, hey, this is removable. This is a hole that's not necessary. Without it, our function's practically the same. The only difference between this and this is a single point. And that single point doesn't really change anything in the sense of the limit. Does that make sense? So having said this then, this gets applied when we start talking about the derivative, right? We have the limit definition of the derivative. I think that was chapter 3. So the derivative of a function is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So really quickly, just refreshing everything. This is like y2 minus y1. And this is like x2 minus x1, right? All we're saying is we want the difference in our x values to go to 0 and find out what that slope would be, right? So this is the slope of the tangent line of the line tangent to our function at some x value. Now let's say we were given the function g of x is equal to x squared plus 2x minus 3. The derivative of this thing is equal to the limit delta x goes to 0, g of x plus delta x minus g of x, all divided by delta x. Now we can rewrite this. This is the limit as delta x goes to 0 of x plus delta x squared plus 2 times x plus delta x minus 3 all minus x squared plus 2x minus 3 divided by delta x. So when we expand this out now, I need room, so I am erasing some of this, moving over to this other side of the board. This is going to be the limit as delta x goes to 0, x plus delta x, that quantity squared, is going to come out to be x squared plus 2x delta x plus delta x squared, 2x plus delta x is going to be just 2x plus 2 delta x minus 3 minus all of this stuff over here. This x squared plus 2x minus 3. Now we're going to divide all of this by delta x. But notice, we can distribute the negative sign all the way through in our second term, right? And we can drop all the parentheses. So we have x squared plus 2x delta x plus delta x squared plus 2x plus 2 delta x minus 3 minus x squared minus 2x plus 3, all divided by delta x. This looks atrocious, but we've got a bunch of cancellations here. First cancellation we're going to have is our x squareds. The second cancellation we're going to have is our 3's. And that is it.
About 2x.
Oh, yeah, you're right. We do have that 2x. You're right. You are correct. I was looking for it. I knew there was another cancellation in here. Yes, we have the 2x as well. So now what we've got is something a lot more manageable. It's the limit as delta x goes to 0 of 2x delta x plus delta x squared plus 2 delta x, and that's it, all divided by delta x. But we've got some more cancellations now, because we can group all these delta x, right? We can factor out a delta x up here and get the limit as delta x goes to 0 of delta x times the quantity 2x plus delta x plus 2, all divided by delta x. So our delta x's cancel. And what we're left with is the limit as delta x goes to 0 of 2x plus delta x plus 2. This delta x is the only delta x, and it's going to 0. So this comes out to be 2x plus 2. Which is exactly what our derivative rule would tell us here, right? If we were to apply the power rule to g of x, we'd get 2x plus 2, which is exactly what we just got down here. Okay, so now we got the derivative of this function. G prime of x is equal to 2x plus 2. Now let's find the line tangent to our function. That's right, tangent line equation at x equal to 1. All right, so a minute ago, I said the derivative is the slope of the tangent line to our function at a point, right? So what we're looking for is going to be the equation of this line. When f of x, or means g of x, g at 1, my mistake. We want to find the equation of this line here. Okay. So to do this, we need to recall what point slope form is. Point slope equation of a line that equation was y minus a particular y is equal to the slope times x minus that particular x, the corresponding x, right? So what that means is we're gonna have to go back to the derivative and plug in 1, right? I gotta run over here. So m is going to be equal to the derivative at x equal to 1. And y naught is going to be our function when x is equal to 1. So plugging in 1 into our derivative, we get 4, because it's just 2 plus 2, right? And plugging in 1 into our original function, that's 1 squared plus 2 times 1. So that's 1 plus 2, that's 3. And this thing is going to be 0. Make sense? Now, we're going to put all this together. We know that y is just going to stay as y. We know y naught is 0. We know m is 4. X is going to stay the same. And we know x naught is 1. So rewriting all of this, we get y is equal to 4x minus 4. So we come over here, and we say the equation for the tangent line at x equal to 1 is y is equal to 4x minus 4. So we just went over the limit definition of the derivative, and how to find the equation of a tangent line for an equation or for a particular function at a particular point, right? So let's check out another problem. What's out there? Is there anything in chapter 2 I wanted to hit on? already hit on it. We already hit on it. My mistake, chapter 2 was the limit definition of the derivative, not chapter 3. Chapter 3 is all about the rules of the derivative. Chapter 3 is all about the ideas like the derivative of a function plus another function is equal to the derivative of each of those functions added together. So just a notation in case anybody has forgotten. Excuse me. ddx of a function, sometimes write using that prime, right? The derivative of the product of two functions is equal to the second function times the derivative of the first function plus the first function times the derivative of the second function. And of course, because this is addition, the order doesn't matter, right? We can write it either way. Chain rule told us that the derivative of a function composited with another function is equal to the derivative of the first function, leaving that second function alone, times the derivative of that second function. The derivative of a constant is 0. The derivative of x to the nth power is n times x to the n minus 1. The derivative of an exponential is the exponential. The derivative of a logarithm, a natural logarithm, is 1 over x. I'm trying to remember, was there any other forms we went over in this class? I don't think there was there? constant, polynomial terms, exponential terms, logarithms. I think that was it. Got the product rule. I should write this as plus or minus, right? This is a sum and difference rule. I think that was everything. Yeah. So with that in mind, the integral of the derivative of a function well, that thing just undoes the derivative, right? What else was there? I think this was the big stuff by and large, right? So things I would suggest everybody check out. Related rates. Chain rule. Graphing functions from their derivatives. The fundamental theorem of calculus. Marginals. Changing the base of logarithms. The derivative of a to the x and the derivative of logarithms other than the natural logarithm. Remember, for the derivative of logarithms other than natural logs, we use the change of base formula. And for the derivative of a to the x, we just rewrote this in terms of the exponential and the natural log, right? We took advantage of the fact that a to the x is equal to e to the ln of a times x, right? That was how we were able to find the derivative of this thing. exponential growth and decay problems. What else can I think of? Integration by parts. I think that was at the very end of 5, right? Let me double check this really quick for everyone. Yeah, exit out of that, okay. Yeah. Integration by parts will be the only thing from chapter 6 you need to worry about. The only thing from chapter 6 will be integration by parts. What else can I recall? Lines tangent to a function. At a point, well, just tangent to a function. Same thing. I think we pretty well covered it with this. Yeah? Trying to think of anything else. Pull up the book really quick. Book. Yeah. Go to limits, obviously. Oh, the quotient rule, yeah. Limits. Quotient rule. I'm trying to make it as exhaustive of a list as I can for y'all. Chain rule and implicit differentiation. Oh, I already got chain rule up there. Implicit differentiation. And area bounded between two functions. And that is the most exhaustive list that I can come up with of things to make sure you review for. There may be things outside of this, but these are the big ones to focus on and pay attention to. Having said that, any questions? The exam will be about 3 hours long and expected to be in the range of about 20 questions. 20, 25, somewhere in there. You can take it anytime next week. But once you start it, you have to commit to it, because if you close out of that window, it may or may not let you go back to it. And if it does let you go back to it, the time that you have lost with that window closed will still be counted as time against those 3 hours. You will have until Friday to take it. I will make myself as available as possible as well this week to y'all. Well, next week, I mean. I only have one day, first thing Monday, actually about midday Monday, that I won't be available. But any other time next week I will be. So having said that, y'all are free to go.